So today I will speak about stability and Lyapunov-Krasovskii methodology for robust stability analysis of time delay systems. This is a joint work with Fabian Wirth, Antoine Chaillet, and Luca Brivadis. So today we will speak about time delay systems of this form. So here xt denotes the state of the system at time t, and it comprises the part of the trajectory from time t minus theta to t, and theta is the maximal fixed time delay of the system. U is an external input, which is essentially bounded Lebesgue measurable function, so from the class L infinity. So this space of continuous functions from minus theta to 0 will be our state space, which we denote by x. And here you see basically how the dynamics looks like. So we take x0 as initial condition, and then we have this, let's say, evolution of time delay system. Okay, so just to make the basic assumptions, we will always assume that f is continuous in both variables jointly. Also, we assume that f of 0 is 0, and f is Lipschitz continuous on bounded subsets with respect to the first argument. So as we know, this guarantees that for any initial condition x and for any input u, there is a unique maximal solution, which we denote by phi of xu. And it is defined on some subinterval of R plus. So phi is the whole state. So this is this continuous function from minus theta to 0. And we would need, in many cases, also the right point of this state, and we denote it by phi 0. Okay, also in addition to existence uniqueness, we have so-called boundedness implies continuation properties. So namely, if the solution is not defined on the whole R plus, then it must exhibit the blow up in finite time. Okay, so these are the basics. Now we would like to study stability of time delay systems, and to this end, we need to introduce some auxiliary functions. We will say that a function gamma is of class k infinity if it is 0 at 0 and increases to continuous and increases to infinity. Beta is a function of two arguments. Beta is called of class KL if it is 0 at 0 and continuous and increasing with respect to the first argument, and continuous and decreases to 0 with respect to the second argument. Now we introduce some basic definitions for this talk. First is one which is familiar for us. So here we set input to be 0, and we say that a time delay system is uniformly globally asymptotically stable at 0 if the norm of the trajectory for a 0 input is upper bounded by a KL function of norm of initial condition and time. So here the larger is the norm of initial condition, the larger will be the bound. And the larger is time, the smaller will be the bound, and it decays to 0 when time goes to infinity. In particular, this means that every uniform globally asymptotically stable system for 0 input is also uniformly attractive. Okay, but we're going to study the systems with inputs. Therefore, we need another concept, and which is natural for this seminar series, we will introduce the concept of input to state stability. A system is called input to state stable if the norm of the trajectory is upper bounded by a sum of two functions. One is beta function, KL function, which describes the transient behavior of the system. And the second is a k infinity function gamma, which is called asymptotic gain, and it describes the asymptotic deviation of a system from the origin. So if u is identically 0, then we clearly obtain that the previous definition, that our ISS system is uniformly globally asymptotically stable for 0 input. And we have the picture which we had at the previous slide. If u is non-zero, then we cannot guarantee that trajectory converges to 0. However, it will eventually converge to the ball with the radius gamma of norm of u around the origin. This fact that input to state stability unifies both internal stability in the sense of Lyapunov, like global asymptotic stability, as well as the robustness with respect to external inputs, has made ISS extremely important for control applications, in particular for robust control and observation of nonlinear systems, for analysis and control of large-scale networks, for controlling presence of delays, quantizations, etc. So there are several books and review papers on input to state stability, and let me just note these two most recent ones, like this book on ISS and this survey on ISS of time delay systems, which appeared in MCSS in this year. Okay, now we have defined what is input to state stability, and now we need tools how we can analyze this property. And as we know, one of the key tools in the time delay systems theory is the Lyapunov-Krasovskii functions. And if we use them for input to state stability, we call them ISS, Lyapunov-Krasovskii functions. So a continuous function we call ISS Lyapunov-Krasovskii functional if V is sandwiched between two k infinity functions psi1 and psi2. And note that above we have the uniform bound in terms of the norm of the state, but below we have a bound in terms just of the absolute value of the right point of the state. So basically, if the norm can be non-positive, but if x0 is 0, then v of x can still be 0. Right? And another property tells the following: if the norm of the state is large enough and compared to the norm of the input, then the derivative of a Lyapunov function along the trajectory, so the LE derivative, is negative and has uniform decay rate, which depends on the norm of x. So basically, it has quite strong decay rate in terms of x, not in terms of Lyapunov function, not in terms of the right point, so let's say current position, but in terms of the whole state. And we need this decay, according to this definition, if the whole norm of the state is larger than norm of u. Okay, so this is the definition which was introduced by a paper in Zhang in 2006, and one of the results in that paper shows that if there is such an ISS Lyapunov-Krasovskii functional, then the time delay system is input to state stable, which is very nice. After some time, there was also a converse result, which shows that for every input to state stable system with Lipschitz continuance F, there is the corresponding ISS Lyapunov-Krasovskii function. So we have really a great property. We have full characterizations of the ISS concept by Lyapunov-Krasovskii functions. However, if we now go back to classical theory of delay systems without inputs, then we see the following. If we have zero input, then one can call V UGAS Lyapunov-Krasovskii functional if V is again sandwiched between these two functions psi1 and psi2. And what is important, now the derivative of a Lyapunov function along the trajectory must decay, but the decay rate is not in terms of the whole norm of the input, but we have much weaker decay. We have decay in terms just of the absolute value of the right point, which is much better. So it's much easier to verify such an inequality, and it's much more handy to use in practice. And we have the classical Krasovsky result, which is also can be found in books, let's say by Hale and Brunel, that existence of such Lyapunov-Krasovskii functional implies uniform global asymptotic stability for zero input. And now we see really a big difference, right? So for ISS, those definition which I have just pointed, it required the dissipation in terms of the whole norm of the state. And here, much weaker decay is possible. And so Antoine Chaillet, 7 years ago, posed the conjecture that, okay, maybe it's enough to have a much weaker dissipation rate also for ISS. And to be more formal, what was proposed that if F is Lipschitz continuance in X, then probably it is enough that V is a continuous function, again sandwiched, and such that we have such an implication. And here there are two things. On the one hand, it is conjectured that it is enough if the Lyapunov-Krasovskii functional decays in terms of the decay of the right point of the state. And also, this decay must be valid only if the absolute value of x0 is larger than u. So see, this happens much more seldom. So we don't require that we have this decay if the norm of the x is larger than norm of u, right? So we require only it under much weaker condition, that if only this guy is greater than the input. Okay, well, this is conjecture, it's not a result. And there were many efforts during the last 7 years to prove this result. In particular, the similar conjecture was proved for so-called integral ISS property by Chaillet, Guexu, and Pepe already 2 years ago. And for input to state stability, this result was proved only under quite strong restrictions on the right-hand side. See, for example, this paper and also several other works. So this paper by Chaillet, Pepe, Maison, and Chitou. Okay, so what we would like to do today, we would like to prove the result which comes close. It's not full proof of this conjecture, but at least this is the closest result which we were able to get right now. But to show that, we need some preparations. Okay, I will start with a very simple observation. We have our time delay system and we study it for zero input. And we assume that we have a continuous functional v, which is again sandwiched as usual, and whose derivative is always non-positive for all x. Input is zero, right? Then it is easy to show that our system is globally stable and we have such a bound for norm of the state at each time t. Let us see this proof, which is just a couple of lines. First, we see that since our derivative of a Lyapunov function is always non-positive, then we have that v at state at time t is less or equal than v at initial state, right? Now we use sandwich bound here. We use sandwich bound from below from that side. Since psi1 is a k-infinity function, so increasing, we can take psi1 minus 1. We do this. We obtain that the absolute value of phi 0 is bounded by this guy. And now we can just take the supremum over all t, and we obtain precisely this result, which is easy observation, elementary. However, now what we see here, this is indeed global stability, but in fact, this property which we obtained just as a byproduct is actually stronger. So if we have this, then we were able to proceed to this property, to global stability. But if we have this global stability, we cannot show this inequality in general, even if we add some k-infinity functions here. Why we cannot do this? Because if we have this inequality, we can again use sandwich bounds so as to estimate it from below by some Lyapunov function scaled. But we cannot proceed from here also to Lyapunov function. We cannot estimate this guy from above by Lyapunov function because v is larger than value psi1 of the value of x0 and not larger than psi1 of the norm of x. So actually this property is stronger. And this motivates actually to introduce alternative stability properties for time delay systems, which are expressed not in terms of the norm of the corresponding states or inputs, but in terms of the functions v depending on the states. So let me proceed to these definitions. I will call v sandwiched if there are k-infinity functions so that we have such estimates, which we had in all our definitions for Lyapunov-Krasovskii functions. Also, we define now, we say that the system is V-ISS if there is, again, the KL function beta and K infinity of K function gamma, such that, and now what we have here, instead of norm of phi, we have here V, this function, and here we, again, instead of the norm of initial condition, have V of X. Okay? This is my definition. So basically the same as ISS, but instead of the norm, I take this function V. And I would like to measure the dynamics, study the behavior of V of my state and not of the norm of the state. It is easy to see that this property is stronger than classical input to state stability. We just use here sandwich bounds from below, and then some tricks are still needed. But afterwards, we get that V-ISS always implies input to state stability. It is a stronger property. Similarly, we can define uniform global stability, well, V-UGS. Again, so we say that a time delay system is V-UGS if this function V of the state can be upper bounded by K infinity function of V of initial conditions plus this gain from the norm of U input. Okay? So this is like similar to input to state stability, but we do not have here decay of this term with respect to time. It only gives us the constant, well, for a given X, the constant upper bound for our trajectory. So it's natural to call it V-UGS, V uniformly globally stable. And the final property which I introduced here is so-called uniform limit property, and again for this V. This property tells that we have some asymptotic gain gamma, and also for every epsilon and every r, there is some time tau, such that if my V of X is less than r, and norm of U is less than r, then I can find time such that my V of trajectory falls into the epsilon neighborhood of gamma of norm of U. So it's not really convergence, it's just crossing the boundary. Let me, this property will be important in the sequel, so let me tell more about this. So this is again just this definition. And now what it tells? It tells that there is some gain gamma, okay? Then for all epsilon, all r, I have this time tau. And so that if I start somewhere, so that V of X is less than r, and I apply input magnitude less than r, I can find time. In this time, always uniform, has uniform upper bound by this tau, such that V lands into this epsilon neighborhood. So here I have chosen, you see, gamma of norm of U is here. I have chosen this is my epsilon. So here I have the gamma of norm of U plus epsilon. And here is my time t, so that my V of the trajectory falls within this epsilon neighborhood of the gamma of norm of U. Okay? Afterwards, the trajectory may again deviate. So it's not like the convergence to this epsilon neighborhood of gamma of norm of U. It's just basically falling down in this neighborhood. Afterwards, it goes away, but then afterwards, it must again converge to the same neighborhood within the same time. And if I take instead of epsilon, epsilon over 2, then I have again some larger time so that I always fall into this neighborhood, right? But then again, I can deviate. So it sounds like butterfly swimming. So the swimmer dives into the water, but then it comes out from the water. But again, within some given time interval, it must dive again and then again comes out. This is this kind of property. If we have no inputs, this is usually called uniform weak attractivity. So it's not attractivity, but something close, therefore weak. Okay. Also, in the stochastic systems, there are the related concept of recursivity of the set. Okay, so this is this property. And now what we can say, and I will not tell much on that, but one can prove that for time delay systems, V-ISS is equivalent to V-UGS, so uniform global stability, plus V-ULIM, that butterfly swimming property, let's say. Okay? I will not go into the proof of this result, so it is basically a specially tailored version for time delay systems of the general ISS characterizations which were shown with Faber and Wirth several years ago. And also, I don't want to tell a lot because there will be a talk by Fabian in 2 weeks where he will explain many things about superposition theorem for time delay systems. So here we will use this as a tool. So leave it without the proof. What I can say that for ODEs, this can be improved. One can relax and instead of uniform limit property, have so-called non-uniform limit property. And it is not possible for infinite dimensional systems to relax, to kill this uniformity. But for time delay systems, the answer is really interesting, and you can learn it in 2 weeks. But for today, I will use this result for developing Lyapunov-Krasovskii theory. Okay. Now I need, before we proceed to ISS, we take some simpler thing. We would like to characterize this V-UGS. And we say that a continuous function is UGS, Lyapunov-Krasovskii functional, if V is sandwiched. And if V of X is large enough and compared to U, then derivative of V does not increase. And, well, we have seen something like that in our observation for zero input. If input is 0, then this is always valid, and we have always that V is non-positive. And we have seen it is then uniformly globally stable for 0 input. After some effort, one can show similar result for systems with inputs. So if we have such a functional, then we have that our system is even V-UGS. It is stronger than just UGS. Okay. And now I can formulate the main result. We will say that a continuous functional is ISS Lyapunov-Krasovskii functional. So basically we redefine it. If V is sandwiched, again, between psi1 and psi2, and now for all X and all U, we have 2 implications. One of them is precisely what was in Chaillet's conjecture. So it tells that if the right point of our state is large enough than input, then V dissipates. So the energy of the system dissipates. The Lyapunov function decays in terms of not the norm of X, not V, but in terms of norm of X 0. So it has very weak type of dissipation. But also we need that if V of X is larger than this norm of U, then V at least doesn't increase. So we have this additional property which we need here. And then we can prove the result. Then we can prove that existence of such an ISS Lyapunov-Krasovskii functional implies not only ISS, but also V-ISS. So stronger property. Well, let us see that, first of all, just from this second implication, we already know that our system will be V-UGS. It's already uniformly globally stable. So in view of our characterization of V-ISS, we need only to show that it has this V-ULIM property. And now I would like to go a bit more into details. So the proof goes as follows. We argue by contradiction. We assume the time delay system does not have V-ULIM property with a fixed gain psi2 of 2 he, where he is the Lyapunov gain as in the definition of ISS Lyapunov-Krasovskii functional. So here was our function he. And also V-ULIM doesn't hold with this gain and with some function tau with this timing, which will be fixed later. So what does this mean? This means that there are epsilon and r positive numbers, as well as initial condition x, such that V of x is less than r, and also an input, such that V along the trajectory is always higher than epsilon plus this gain, overall interval from 0 to tau. Okay, so by V-ULIM property, we had to land within this epsilon neighborhood of the gain. And here, since we argue by contradiction, we say that we are always above this epsilon bound. Now we use sandwich estimate, so we can upper bound V from above by this psi2 function of the norm of the state. Taking the inverse of this function, we have that the norm of the state is upper bounded by this guy. So instead of sum, now we take the maximum here. And what does this mean? So we have that the norm is larger, right? So it doesn't mean that at each point, the trajectory will be larger, but that in each segment of the length theta, our maximal delay, there is some point such that such an inequality holds, yeah? Okay, now what do we do next? So this inequality holds only pointwise, but what we would like to show that some similar inequality holds on some time segments. Let us do that. So first of all, one can show after some effort and using V-UGS property, which we have already proved, that the maximal speed with which the trajectory changes can be upper bounded by this term. And here is very important that we have here bound in terms of V of x and not only of the norm of x. This is how V-UGS helps us. And why do we need bound in terms of V of x? Well, this is because our initial condition satisfies such an inequality. And now we can V of x upper bound by R. And so we can upper bound all this guy by mu of R. So we bound this by R and also norm of U, okay? Where mu is some k-infinity function. So now we have the bound for our speed of the trajectory, how it can change, well, in the right. So what this means? This means now that after some effort, one can show that actually phi 0, so our right point of the state, is always larger than this term for times in these time intervals. So earlier we had that phi 0 is greater than something here only at point tk, but now we could prove such an inequality on a certain segment around tk, which is what we will exploit next. What we also know, we know by our assumption that the system is not VU-Lin, that phi v along the trajectory is upper bounds here of norm of u. But now, since v is a ISS Lyapunov-Krasovskii functional, this means that along the trajectory, the derivative of v on this segment does not increase. Okay? And now what we would like to use, we would like to use this estimate on the whole interval plus this estimate for these segments. Let us see how this works. So v of phi at time tau minus v of x can be written as such an integral, right? Now we upper bound this integral in this form. So what we do, we just use that v dot is less or equal than 0 on the all along the trajectory. So I threw away all the intervals we are not interested in, namely all the intervals which are not on this form. And we just upper estimate this integral as the sum of integrals over these subintervals. Now, at each of these subintervals, we can upper bound v dot with our pointwise decay rate. And moreover, we know that phi 0 at these intervals can be also, well, lower bounded, and thus minus phi, norm of phi 0, can be upper bounded by such a guy. And what do we have now? Now we have this sum. So let us now count how many points are there in this interval. Well, we have tau minus theta divided by theta is the number of points tk. Well, this is, let's say, the minimal number of points. We know that in each segment, there is at least one of them. If more, good for us. But at least one there is. So we have at least this many points. Also, for each point, we have at least one, well, we have one segment, right? And the length of this segment is precisely this guy. And at this segment, we have the value which we integrate is this guy. So overall, this can be well, okay, less or equal than this guy. And now what we have obtained, we can now put V to this part, this guy to above, to another part, and then we will see that R is greater or equal than V of X, and it is greater or equal than this guy. And now choosing tau in the right way, we can ensure that this term is actually will be larger than R. And in this way, we will violate this inequality and get to a contradiction. And this is what we do. So we choose R in this way, tau in this way, and then we obtain a contradiction to this inequality. This contradiction shows that our time delay system has V-Lim property. And finally, by V-ISS superposition theorem, we obtain that V-UGS together with V-Lim implies V-ISS. And now let us compare to what we had previously in previous results. So the first ISS Lyapunov-Krasovskii theorem due to paper and Jung stated that if F is Lipschitz, V is sandwiched, and we have such an implication. So we had dissipation in terms of the norm, and also the dissipation must occur if the norm of X is larger than input. Then we have ISS. Then this result was improved by Kankana-Malage, Lin and Wang, who have shown that, okay, if we assume a bit more from F, that it is Lipschitz in X and in addition in U, then it's enough that we dissipate in terms of the right point. And the dissipation should occur if V is larger than norm of U. And they have used completely different proof technique, which, okay, for those of you who knows, it resembles the proof of converse Lyapunov results for ODE systems, let's say, and for other types of systems, like that ISS implies existence of a corresponding Lyapunov function. But here it is used in different way, but similar idea. And now what we can show, we can improve this previous result in several respects. First of all, we don't need Lipschitz continuity in U. It's enough to have only Lipschitz continuity in X. Also, our dissipation is also in terms of the X of 0. But we must dissipate only if absolute value of X0 is larger than U. So we don't need that V of X is larger than U, which would be a stronger requirement. We need weaker dissipation, but we still need that if V is larger than U, then at least V does not increase. But also, in the end of the day, we obtain not only ISS, but a stronger property of V-ISS. Also, I would say that the proof is a bit conceptually simpler if we assume that this V-ISS criteria are already given for granted, that we have all of them. Then it looks like a bit short, and also it looks closer to the original proof by Krasovskii. At least for those proofs which are, let's say, in books by Hale, Lunel, and other classical references. Okay, so now what we have here, we have some open problems, right? So this is what we have proved. But what was the original conjecture was that probably we can possibly exclude this at all. Maybe it's enough to have just this to get input to state stability. We don't know. We were not able to improve our technique so as to kill this implication and not require that. However, now we still have a hope that it could be possible, because what we obtain in the end is not only ISS, but V-ISS, a stronger property. However, here's the main problem. How to define the Lyapunov functional for uniform global stability? So that we can obtain only UGS and not something stronger. So we need somehow to think how we can redefine the UGS Lyapunov-Krasovskii functional, and it somehow looks unclear because this is like a natural requirement. It is used for ODEs, for other types of infinite dimensional systems, and there is, well, it's not fully clear how we can modify it, at least. If you have any ideas, it would be great to know. Well, These were open problems. Now let me show also one consequence. We can strengthen Krasovskii original theorem. Namely, we consider the time delay systems, now with inputs. So note that original Krasovskii theorem was for system without inputs. And here we define V-UGS in our fashion. So again, as uniform global asymptotic stability, but instead of the norm, we'll have this function V. This is again then stronger property than just UGAS. And also note that we want to have this for all inputs U. So it's like V-ISS with zero gain. Or you may understand this is like uniform global asymptotic stability, but robust with respect to all inputs. Then we can introduce the UGAS Lyapunov-Krasovskii functional in this way. So V is sandwiched and V dissipates, has this pointwise dissipation. And then we can again show that existence of such UGAS Lyapunov-Krasovskii functional implies V-UGS of time delay system. So we have basically two improvements. One of them that we can obtain the Krasovskii result for systems with additional disturbances. And second, that we can get a bit more than UGAS. We get V-UGS. Okay. Now I come to my last slide. Namely, what we have shown. Well, one, the result which is important by itself, which is ISS superposition theorem with this additional V functions. And we have used it to get the, let's say, best approximation to the Chaillet conjecture which we have obtained. So if Lyapunov function dissipates, has pointwise dissipation, and if this dissipation is activated only if pointwise we are larger than U, and if in addition V is a Lyapunov-Krasovskii functional for UGS property, then we have V-ISS. Also, what I can say that this development of Lyapunov-Krasovskii theory, or let's say refining this theory, is a part of our program on development of theoretical basis for ISS theory of delay systems. And there will be two other talks in this seminar series, one by Fabian Wirth in 2 weeks, in the last day of January, where Fabian will present what should be the tight characterization of input to state stability property for time delay systems, whether we can relax, for example, here, uniform limit to just limit, where we can relax this property or not. So the corresponding result was something, well, what not could be like clear from the very beginning, I would say. I find it quite interesting. And so please, if you would like to know, you can come to this talk by Fabian. And also there will be a talk by Luca Grivadis, who will analyze whether forward completeness tells us something about reachability sets of delay systems. Quite recently, Jose Luis Mancilla Aguilar and Hernan Haimovich have provided a counterexample which shows that if we have delay systems and the state is continuous functions, then just forward completeness does not imply boundedness of reachability sets if we have a state space as continuous functions. Interestingly, if we take the state space as Sobolev space, then forward completeness implies boundedness of reachability sets. So we have really two different results. If we, for continuous functions, it does not imply, and we have counterexample, and for stronger, for like better state space, forward completeness implies boundedness of reachability sets. What we wanted to study here and what Luca will present is what happens if we take a larger state space, not continuous functions, but all L infinity we take as a state space. And it will be quite interesting. I will not tell you what will be the answer in this case, but you can see it on 14th of February. So at this point, I would like to close this presentation. Thanks a lot for your attention, and I'm looking forward to your questions.